lecture of today. And actually today is not a lecture, it's the physics colloquium. I think, okay, no. It's the physics colloquium. And usually when there is a school, the physics colloquium is given by a professor of the school. And today you have the pleasure to have Xiaoming Mao, which is my pronunciation, my you know, English, Chinese, Portuguese style of pronunciation. And okay, thank you. And then she's from the University of Michigan, and I guess most of you know her already because she's have been teaching us. So please, Xiaoming, you have 1 hour or an hour and something to.
Okay, can you all hear me okay? Yes. Okay, yeah, thank you. So it is my great pleasure to give the colloquium today, and I've been having a lot of fun knowing all of you, and yeah. So today I'm going to talk about some of our recent work trying to bring together many different ideas from geometric frustration to self-assembly mechanics, and try to explore how by bringing these concepts together, we can think of new pathways to complexity. So let's start by looking at some pretty pictures from nature. So what you're looking at here is coccolith, which are these tiny little structures you can find at the bottom of the ocean. And the scale bar here is 1 micron, so 10 to the minus 6 meters. And these structures are made by single-celled algae called coccolithophorus. So these coccolithophorus take calcium from the ocean and make them into these little platelets and use that as armor to protect themselves. So it's really interesting to look at. And the material here is calcium carbonate. So I'm not sure if everyone is familiar with this material. It is a material that we use to make a chalk. So normally we would think it's a boring material. It's what could be too special about this? However, in the hand of biology and the biomineralization, this seemingly boring material can take all these interesting morphologies. As you can see here, regular dodecahedra, minimal surfaces, and these complex hierarchical chiral structure. So it is really amazing to think about how these structures form from this interesting process in biology. And this is definitely not a single example of complex structures in nature. There are many, many more examples. Just to give you a few more, the structure of our hair and the bones. At the macro scale, they may appear to be boring, homogeneous material, but as you look into the microstructure, there are several hierarchies of complex structures. And these are all demonstrations of how we can find fascinating, complex hierarchical materials in nature. And recently, my group has been becoming really interested in these complex structures. How do we describe the order in these structures? They are obviously not crystals, but at the same time, they are not amorphous either. There is some complex hierarchical structure in them. And when we describe these structures, we think about how this complex order offers us with physical properties. How do we link the structures to the properties? And why do they have to be so complex? What is the purpose of having this complexity in nature? And how do we learn about the mechanism of how they work? And can we use that to design new metamaterials or artificial structures? These are all like the overarching questions of something we're thinking a lot about recently. And today I'm going to talk about just some baby steps we are taking towards understanding this complex order in nature. Okay, so to start, I would like to just talk about some basic concepts. So what do we mean by structural complexity? What do we mean when we say the structure of one material is more complex than the structure of another material? So let's think again about 2 simple limits. one ordered limit where you have crystalline structures, perfectly long-range ordered. And in the other extreme, you have disordered materials such as glasses. If you measure the complexity using quantities such as information entropy, you would say this is much more complicated than this, because information entropy basically measures how much information you need to describe the structure in the most compressed way, right? So if you try to write a code to exactly regenerate the structure, here you only need a few lines to write a crystal. But here, the length of the file is proportional to the system size. So you have a lot of detailed information here. However, although there is a lot of information, not all of the information is useful in predicting its properties, right? So most of the properties that are relevant to what we're interested in, we can often write some effective theory to describe it without the need of using all of the detailed geometric information. So then in this sense, this limit is not that much more complicated than this limit. However, in the middle, between order and disorder, there are structures that are truly complicated and cannot be described by simple effective theories. And these examples basically speak for themselves, right? So to capture this concept, this idea called effective complexity or non-random information has been proposed, to my knowledge, first in this book by Mary Gell-Mann, who was a Nobel laureate. And this also relates to earlier work, for example, related to Kolmogorov entropy, where you want to capture the non-random, useful complexity, the information into the problem. And Mary Gell-Mann proposed that in the middle between order and disorder, there is this so-called Goldilocks zone, where effective complexity peaks, and you have the best efficiency, robustness, adaptability, and multifunctionality. And he also argued that our nature is running at this Goldilocks zone. So of course, this is an interesting idea to think about. And the examples I included here are all from nature. And you can imagine they are all perfected through many generations of evolution, right? And for us as physicists and engineers, one interesting question we can ask related to this is, can we assemble these complex structures without the biology in the lab? For example, using inorganic nanoparticles, how do we program the assembly of these complex structures? Or in other words, you can ask the question as, are these complex structures completely hard-coded from the biology? Everything need to be from some genetic information, or you only need a little bit of genetic information. The rest of the job can be done by physics, chemistry, and geometry. Somehow the system can assemble itself into these complex ways. So how do we think about that? How do we tune between order and disorder? There are different types of pathways you can think about, right? So from the point of view of condensed matter physics, one obvious pathway we can think about is to gradually introduce disorder in an ordered crystal, right? You can put in defects and grain boundaries, and as you do a lot of that, you go to an amorphous state. This is a relatively straightforward pathway, but there are other pathways. For example, you can go out of equilibrium and consider far from equilibrium pattern formation problems, like in this picture, or turbulence. These are all mechanisms that can take you sort of continuously from order to disorder, and you can get interesting complexity coming out. And another pathway is, of course, biology, like we just mentioned. And what we are going to talk about today is a relatively new pathway between order and disorder, which is geometric frustration. We would like to argue that geometric frustration gave us a somewhat continuous tuning knob that can help you go from order to disorder and study how complexity proliferates along this pathway. So how do we think about that? What do we exactly mean by geometric frustration? So when you mention the word geometric frustration to a physicist, this is usually the picture that emerges. And we actually looked at pictures like this in the morning in Corentin's lecture, right? So the geometric frustration I'm going to talk about here is a different type. It's a more purely geometric problem. So you think about taking regular polyhedra in three-dimensional space. There are 5 of them: tetrahedra, octahedra, icosahedra, cube, and dodecahedra. Okay? So if you try to imagine taking these regular polyhedra and pack them in three-dimensional space, which of them can pack with 100% volume fraction? Which means no gaps, no overlaps. You just perfectly pack them, covering space. Any guesses? The cube can do it. Anything else? So it turns out that only the cube can tile space. Everyone else is frustrated. So how do we think about that? You can think about this question by looking at the dihedral angle of these polyhedra. And let's take a tetrahedra as our example. So when you take the tetrahedra, you can try to pack them together, right? You can, for example, take 5 of them and pack them around an edge. And when you calculate the angle between the 2 faces on a tetrahedra, you will see that it is slightly smaller than 2 pi over 5. So you will have a little gap that cannot close. And when you try to pack 20 of them together around one point, you will see that you almost get an icosahedra. But again, you have small gaps because the angles don't fit together. And similar things happen when you try to pack these other shapes. So they are all geometrically frustrated when you try to put them together and tile three-dimensional space. So then these are ideas that have been known in mathematics for a long time. And in fact, they have been used in condensed matter physics to understand a number of important problems. For example, one of the early theories for glass transitions proposed by David Nelson and others make use of this idea of the fact that when you try to pack spheres in 3 dimensions, it is geometrically frustrated. It is, in fact, the same type of geometric frustration as packing tetrahedra. So packing of spheres and packing of tetrahedra are actually dual problems to one another, in the sense that you can take a tetrahedra and put spheres on the tip of each vertex. Right? And you choose the radius of these spheres such that they are exactly touching one another at the middle of the edge. And then there is a translation between the sphere packing problem and the tetrahedra packing problem. Both are frustrated in exactly the same way. So there has been theories making use of this frustration to explain, for example, glass transitions and liquid crystal blue phases. And more recently, these ideas have also been used in self-assembly problems. For example, in this work from Greg Grayson's group, they look at the assembly of fibers, but these fibers are chiral, so that each fiber wants to twist a little bit relative to its neighbors. And when you try to bundle them together, you get a geometric frustration, and you can only grow a certain number of layers. Beyond that, it's going to be too much frustration. And there are also interesting studies of slightly twisted polygons that cannot perfectly tile space. So you get a self-limited assembly. And here I would like to also mention a more new work experimentally, where people try to crystallize molecules that are chiral. So these chiral molecules have shapes and interactions such that from one layer to the next layer, it wants to twist a little bit. However, we know that for 3-dimensional crystalline structures, Bravais lattices cannot be twisted, right? You can only have achiral Bravais lattices. So when these molecules form large crystals, it's flat, it's totally normal. But somehow, when you form a small crystal like this fiber, it is so small that the system is able to actually twist from layer to the next layer. And when it grows bigger, that twist is overwhelmed by long-range order and it becomes straight again. So these are all interesting examples where geometric frustration shows up in condensed matter problems. So what is a new question we try to ask here? What we try to understand is sort of slightly different from these problems, but think about how geometric frustration can be used to control the complexity of the problem. So why do we think geometric frustration is related to complexity? How does it work, right? So let me try to illustrate this relation using this figure from a recent paper where the authors studied physical foundations of biological complexity. So interestingly, they argued that the complexity in many biological problems originate from some sort of frustration. And the frustration at the very small length scales is the attraction and the repulsion frustration between these molecules, so that it frustrates the formation of long-range crystalline order. So as a result, you get these out of equilibrium glass-like structures, and then self-organized criticality, and then with some complex mechanisms going across length scales eventually to the complex biological world we have today. So this is, of course, really interesting ideas to think about. And for us, we can think like if everything starts from these frustrated interactions, we can take these molecules in the lab, right, and just put them together and see what happens. As you can guess, most of the time, or almost all of the time, you will not get something this complex, right? If you take these molecules and try to cool down them to form some condensed phases, if you cool down really slowly, the long-range order can emerge, you get a crystal, right? And if you cool down really fast, you get a glass. This is typically what happens in condensed matter physics. Why don't we get the complex stuff in the middle, right? So here, to be complete, I would like to mention that in the inorganic world, you can actually have rather complex structures, such as the structures of snowflakes. You have all seen like quite a complicated hierarchical structured snowflakes, right? Which probably has something to do with water anomaly, right? And there are also complex structures such as so-called diffusion-limited aggregation, where you have these micron-sized particles where in an out-of-equilibrium process, they can diffuse and stick to one another, and you get these complex fractal-like structures. However, in both of these cases, the system has to be controlled to be in some out-of-equilibrium condition, so that you can frustrate the long-range order of forming crystals, and somehow the system can be in a kinetic range such that you get this complexity. However, if you think differently from the point of view of geometric frustration, we can ask a different problem. Can we actively use geometric frustration such that we can form complex structured materials in near equilibrium conditions? We don't need to control out of equilibrium growth conditions. We just program how the pieces are frustrated so that it's not possible to get a nice crystal in a very large range of parameters. Okay? So how do we exactly do that? How do we program complexity using geometric frustration? So this leads us to the outline of my talk, and I would like to also acknowledge my collaborators. So I'm going to first talk about recent work we have done on frustrated assembly of non-Euclidean crystals of tetrahedra nanoparticles. This is done in collaboration with my postdoc Francesco, my colleague Nick Kotoff, and his postdoc Jun, and also my colleague Kai. And I would like to also acknowledge ongoing work and discussions with Sharon Glotzer's group, her postdoc Philip, student Yeyin, and my graduate student Nan. And then after that, I would like to talk about some more recent work in studying mechanics of frustrated non-Euclidean systems, basically trying to answer the question, we can always make crystals, right? Why do we want to make things more frustrated and complex? What do we gain? And I'm going to give you 2 examples of our recent work, demonstrate what is the interesting physics you can reveal by introducing frustration in some mechanical problems. Okay, so let's start from the first one. I would like to start by describing an experiment from my colleague Nick Kotoff's group. So in this experiment, they take these nanoparticles, which are made of semiconductor materials. So these are like crystals of nanometer sized. So you can imagine this is a regular tetrahedra that is made of crystalline arrangement of these of these atoms. Okay, and then they graphed the surface of these nanoparticles using some small chiral molecules, chiral ligands. And then they left them in solvent for them to assemble with one another. So basically, the assembly is driven by shorter range van der Waals interactions that pull the particles together. And then the ligands can form covalent bonds with one another, so the particles favor face-to-face binding. And then, interestingly, after they wait for a while, they get a complex spiral-like structures out of this. And just to be clear of the length scale, here, the length scale of these spirals is about 1 micron, and the particles are nanometered. Okay? And as they change the condition for the experiment, they also get other types of complex assembled clusters, such as twisted or untwisted bundles. And in other similar nanoparticle ligand assembly systems, they also get other more complex but quite controllable assembly processes. So when we look at the experiment, it really strikes us to think about how this wonderful complexity come from really simple building blocks. Here you just have regular polyhedra. How does simple regular polyhedra give you all these complex shapes? That was really the question that attracted our attention and motivate us to think about can we write a theory to explain that. Okay? So by the way, if anything is not clear, please feel free to raise hand and ask. Yes?
Just about the basic shape, any facet can attract to any other, or are they different?
They are all the same.
Okay.
Yeah. So it's not a specific interaction. Any other questions?
What variables did you change to obtain different structure?
Yeah, there are actually a lot of parameters you can have. So one convenient parameter is to change solvent properties. Look, they add these ions and other components into the solvent to control the range of the interaction. And so the particles have both attraction and repulsion with one another. You can change the range of these interactions. You can also use different sized particles. You can also use other types of ligands. So there are a lot of parameters you can change. And by the way, I should also mention that this is a very out of equilibrium process. So the attachment of the particles is rather irreversible. So when two particles attach and the ligands form covalent bonds, it's a very deep, it's about like 30 kBT, that it's hard for them to separate. Okay? So that's sort of the basic picture of the experiment. Okay? Yes?
I remember in regular crystal growth, there were some cases where it was easier to grow a crystal around a Scrooge location or something like that. No,
Yeah.
Do you have the same thing here, or do you have topological defects that make it easier?
Yeah. That's a very interesting question. We have not studied, so I think there must be some defects there. But as I will mention next, the crystals here are very strange crystals that are non-Euclidean. So what kind of defects are there is a whole new question, I think, quite unexplored. So yeah, it will be really interesting to look at that. Mm-hmm. Okay, yeah, another question?
If we look at this braid on the left and we zoomed in, what would be the texture of it that we would see?
Yeah, so I will get to that. So basically, it's likely there are many layers. So you have layers of these helicoid-like assemblies, and then they stack with one another. Yeah. So I think it's sort of, maybe some regions are crystalline and some regions are more amorphous in the real experiment. Okay. Okay, so how do we understand the geometric frustration of this problem? So we mentioned a little bit there is a geometric frustration when you try to pack tetrahedra together. So in a little more detail, you can make 1D chains of tetrahedra with no geometric frustration. You can make chains like this, which are so-called tetrahelices. So you can attach them face to face, and then that gives you a straight line like this. The frustration comes out when you try to bundle these 1D chains together. As I mentioned, the angles don't fit together, and you get these twisted bundles that will split further and further away. And I actually have some 3D printed toys that show this behavior. Let me see if I can find it in my backpack. Okay, great. So what I have in this set of demo are 5 tetrahelices, okay? And you can try to bundle them together like in that picture. And what you will see is that you can hold them like very much fitting nicely together in the middle, but then they split at the tail. You can see very clearly how it's frustrated. So I'm gonna pass around, and you can feel how it's like. Okay, so that's the mode of frustration. However, the interesting thing here is that this frustration is an artifact of the flat 3D space we live in. If the space is curved, you can actually close the gaps and make everything nicely fit together. And in fact, when you introduce positive curvature to our 3-dimensional space, what happens is that the gaps close, and then these rings also close to themselves. Everything curves in an isotropic way. And you get these rings of tetrahelices that are tightly bind to each other. So this is quite abstract to think about. What does it mean to curve our 3-dimensional space? To show the concept, here I included a video that show first an example of introducing curvature to a frustrated assembly problem in 2D, where you can very clearly see how introducing curvature solves the frustration. So here, imagine you have a bunch of pentagons, and you try to tile your floor with pentagons, which is, of course, a very bad idea because they don't fit together. You will have gaps. However, if your floor is curved, you can actually do that very nicely. And here I'm going to play the video where you introduce positive Gaussian curvature, everything fit nicely together. What you get is the regular dodecahedra. And in the last frame, what you see is that you can project the shadow of this dodecahedra back to flat 2D space. And what you see here is that the pentagons are really distorted because you're squeezing from 3D to 2D. However, the actual structure in 3D is perfect, right? In the sense that all of the pentagons are perfect pentagons, and they are the same. They have the same number of neighbors. So in this sense, it is like a crystal, right? It has perfect order as you go around to translate around this packing, okay? So then how does it work in 3D? It's actually pretty similar. So now imagine taking these dodecahedra and try to pack them together in 3-dimensional space. So as I mentioned, the dihedral angle here is a little smaller than 2 pi over 3. So when you try to put them together, there are 3 of them, but you have small gaps. And interestingly, I'm going to play this video, which I found on YouTube that very nicely illustrated it. You can have 1D chains of dodecahedra that nicely fit together with no frustration. However, when you try to bundle them together, there will be small gaps, right? And interestingly, you can take 2 such bundles, a total of 120 dodecahedra, and you can introduce a little bit of positive curvature to 3-dimensional space. That closes the gap between the dodecahedra. And at the same time, the thing also closes to itself, and you get this nice crystal that lives in 4 dimensions, which is where all of the nodes are on the surface of a sphere in 4 dimensions, which is so-called 3-sphere. So 3-sphere is the surface of a sphere in 4 dimensions. Here, all of the nodes are on a perfect 3-sphere, okay? And this structure, it is a surface of a sphere, but it's a solid thing in 3 dimensions, okay? So you see that there are layers and layers of these dodecahedra. And in this picture, it looks like the dodecahedra are distorted. They are not equal to one another. That is just the artifact of projecting from 4 dimensions to 3 dimensions. The actual structure in 4 dimensions is perfect crystal again. And it is a finite crystal with 120 dodecahedra. And yeah, all of the nodes are exactly on this 3 sphere. Any questions? Maybe I should play the video again so that you can see how it goes.
So actually, what you call, you start by saying that you would use geometry frustration
Yeah.
to explain this complexity, but actually it's like increasing the space that you are, or allowing for a higher dimension.
Mm-hmm.
Is the thing that you are doing to solve the problem, in the sense that to transform something which is gapped in something that's very well packed, right?
Yeah. So we have not get to the complexity yet. So here we are just illustrating that, as I will show in a few slides, the actual ground state is not in our space. That is like one way to think about this geometric frustration problem.
Okay, I see.
That helps us to build an analytic theory.
So you are calling this form the ground state of our problem. That's the way that you think. Okay.
Yeah, that's right. Yes.
I noticed in 2D and also in 3D. So in 2D, when you curved the space, the superstructure was a pentagon, as was the tiling. And here too, with the dodecahedron, when you do this curving of space, the superstructure is also dodecahedron. Is this a coincidence, or?
Why? Well, what do you mean the superstructure is?
As in the structure formed by all those pentagons in 2D had when you projected it back onto.
Here the faces are pentagons.
Yeah, in the 2D problem, 2D.
In the 2D problem, let me see if I can go back. Yeah.
Yeah, when you project, so when you.
Oh, I see. So I think that has to do with the symmetry of that polytope. So polytope is the generalization of polyhedra in general dimensions. The symmetry of the polytope comes from the symmetry of those components, right? So that's sort of why the overall envelope has the 5-fold symmetry.
I see.
Yeah. Okay. Okay, so we show the video of the packing of dodecahedra into 120 cell. So what happens with tetrahedra is actually very similar. What you get is a so-called 600 cell. I don't have a beautiful video to show that, but the 120 cell and the 600 cell are actually due to one another. So it is exactly the same type of geometric frustration. By introducing positive curvature, you close both of them and get a finite crystal in a positive curvature space. Okay, so these are mathematical concepts that has been known for a long time, right? Mathematicians have been studying these polytopes for a long time. Why do we get interested in these in the context of self-assembly? The reason is that we believe these structures represent the true thermodynamic ground state of the assembly problem. This is pretty easy to see that in these non-Euclidean crystals, the particles attach to one another perfect face-to-face. You have long-range order. The volume fraction is 100%. You can easily show that the potential energy is actually the minimum, and the system is really at its happiest state. The only problem is that this state is not in our space. It's in some curved space, which can be embedded in higher dimensional space, but not Euclidean 3D space. Okay? So to illustrate the relevance thermodynamically of these non-Euclidean crystals, I would like to quote an interesting Monte Carlo study in the 1980s, where the author tried to study Monte Carlo simulation of sphere packings in flat 3D space and on the 3-sphere. So as we mentioned, the packing of spheres and the packing of tetrahedra are dual problems to one another. Actually, the packing of spheres is very similar to the packing of dodecahedra. They want to order into this tetrahedra, into this icosahedra arrangement in terms of its neighbors. Okay? So what the author find is that when you run a simulation on a 3-sphere, when you put these spheres on the surface of a 3-sphere, the Monte Carlo simulation very quickly anneals to the ground state, which is the 120 cell. However, when you run the Monte Carlo simulation in flat 3D space, maybe many of you have already tried that, it's very hard to get the FCC crystal. We know that the FCC crystal is the best packing, but it takes forever to anneal out the topological defects in the problem. So this is a really vivid demonstration that this problem is a happy problem, right? The system very nicely wants to go into this thermodynamic minimum. It's the true global minimum that has a very wide opening in the thermodynamic phase space. However, this problem is so frustrated that the system has a hard time finding the correct state. Okay? So here, as you can see, these are completely different crystalline states on the 3-sphere and the flat 3D space. What we're trying to do here is to see whether we can bring these non-Euclidean crystals to our space in some way. Yes?
On the left of the 3-sphere,
Yeah.
There's this intermediate sort of configuration where it gets stuck at sort of the same energy and then drops down to 0. What is that intermediate state?
Oh, you mean like this? So I think
Yeah,
it is
on the left.
also here.
Yeah.
So I think that is just a numerical thing they do in Monte Carlo simulation to anneal the system after a certain number of steps to see whether it is falling into ordered state. Yeah. Any other
Is
questions?
it possible? I have a question.
Okay.
Is it possible to predict? Let's say this is an example that I know, because it's common for us to try to minimize this for me.
Mm-hmm.
But is it possible, given a structure in the 3D space, is it possible to say that in a given dimension or in a given surface, it would be like at the minimum ground state?
Yeah, you can find that space. So I will actually get there. So basically, you say how you want to pack it locally. And I say I want to propagate this order infinitely far. By setting up such a rule, you can find that crystal and find which space that crystal lives. Yeah.
You say that a problem that is not frustrated is in another dimension, don't have gaps. But what is the meaning? Or what could be the meaning of this gap in our space? I mean, I don't know if you understand the question.
So what does it mean to bring that thing to our space?
Yeah.
Right? Yeah. So I think an intuitive picture is like that. Remember in that 2D example, you have a light and then you see the shadow, right? So it's basically like that. You try to cast a shadow you try to do a projection from a high-dimensional space to our space, where the thing becomes really, really distorted. Right? It's a highly stressed structure. You cannot have the whole thing, but you can cut a part of it and ask what shape does it take in our space. And that's what I'm going to get into. We construct a theory to predict that shape.
Yeah, but there is a physical meaning of these gaps. I mean, a system that is not frustrated in a high-dimensional space, and when we get to our space, we have these gaps.
So you don't necessarily have gaps, right? So you have gaps when the particles are perfectly rigid, right? But if they are deformable, they will be strained, not gapped. Yeah, that's a basic picture that enables us to write a continuum theory. And then later you can consider that actually they are not that deformable. You have to make corrections of the fact that you have inhomogeneity in the structure. Yeah. Okay. So then how do we exactly do that? Here, I don't want to go into too much detail of the mathematics. I will just sketch out the main steps of the theory. So basically, we start from some packing rules for the polyhedra. We say that, for example, 5 of them should assemble together like this. And for each tetrahedra, it should have 4 neighbors on its 4 faces. And then from that, you can construct the non-Euclidean crystal. Okay? In this case, it's the so-called 600 cell. And then you can start from there, try to write a coordinate system and find the metric that describes the non-Euclidean geometry of that crystal. Here, without going into too much detail, this metric is the non-Euclidean metric you can calculate from this crystal. And then you write a continuum theory where you have energies that come from elastic energy cost, which means you take this metric, but this metric cannot be embedded in our space because it has a curvature. So the actual metric the system can take is a compromise. So the elastic energy cost would be how much you deviate from that perfect metric because you are trying to push this structure to our space. And you add that with other energy in the problem like repulsion and the surface energy. And then you put that together, you cut a piece of this non-Euclidean crystal. And in the end, you can do a minimization of the total energy and find the morphology. So here, what I'm trying to show in this group of picture is that the internal structure of the 600 cell can be thought of as 4 toroidal shells that are covering each other and intertwined, tangled together. And for this particular problem, we choose the 2 middle toroidal shells, which are made of 2 shells of perfectly packed tetrahedra. And then the reason we choose these 2 layers is that they have a perfectly smooth surface. So you have low surface energy, and there are other considerations of having homogeneous in-plane metric. So anyway, we can write a low energy theory to describe the elasticity of this object. And then that tells us predicted morphology of how this thin sheet takes shape in flat 3D space. So we can make predictions. So basically, the structure of the theory is that we start from the mode of geometric frustration. We find the ground state in non-Euclidean space, and we use that to make predictions about the morphology. And this morphology is necessarily pre-stressed because the ideal metric cannot be embedded in our space. So in particular, we can quantitatively make predictions. For example, what is the pitch of this helicoid? And we can compare with experiments. So in particular here, the pitch is controlled by both the elasticity parameter and the repulsion, which, yeah.
Quick question. What's the energy landscape? What does it look like? Do you have multiple minima, or do you have just one ground state that governs the, yeah?
That's a very interesting question. I think for this particular section that we cut from the crystal, we have a ground state degeneracy of shifting this, let me see. Actually, this is a unique ground state for this particular problem. Yeah, but you can cut different parts of the non-Euclidean crystal, and there should be many other ground states. We so far just studied this one, guided by what is observed in the experiment. Yeah. Okay. So as you can see in the experiment, they are able to change solvent properties, which control the repulsion between the nanoparticles. And as a result, you see different pitch and different size of the assembled spiral clusters. And we can get some qualitative agreement with our predictions. And again, I would like to stress that here, what we have is a perfect crystalline structure, but the actual structure coming out from the experiment is much more complex. What we have is a very coarse-grained theory as a first step to understand this. And currently, we are working together with Sharon Glotzer's group to do molecular dynamics type of simulations to see how these particles actually come together kinetically. How does it form fibers first and then bundle together, or this whole thing just form at once? And this is one of the examples of the structure we get. As you can see, it is a perfect crystal. You have perfect long-range order. However, this crystal is frustrated such that as you try to make this ribbon wider, there is a lot of stress and it splits, okay? Okay, so this is the first example of this kind of non-Euclidean crystals. And then you may ask, what about other shapes? For example, what happens to these other types of polyhedra? Yes?
Thank you. Maybe there's something I'm missing. So I don't understand why the ground state, when projected to a lower dimensional state, it has a lot of stresses, and I don't understand why is it relevant in this lower dimension. So if we go back to the 2D example that you showed us, curved, if we take the projection of the 3D object to 2D, we see a lot of like very big deformation. So why would it even assemble in anything resembling this shape?
Yeah, so in this particular case, the curvature is actually pretty small, right? As you can see, when you put 5 tetrahedra together, it's just a tiny gap. So energetically, it doesn't cost that much to actually bend things a little bit and make it, force it to close. And as you can see here, this is the perfect non-Euclidean crystal. It's not that much more distorted. The 2D case is actually much more stressed. This one is not super stressed.
Okay.
Yeah, it depends on the energetics and the entropy of the problem. Okay?
Thank you.
Okay, so what about other polyhedra, right? So as we mentioned, you can come up with different rules to pack them. And depending on how many of them you try to close a ring, you can either pack them on the 3-sphere, which means positive curvature, or on hyperbolic 3D space, which means negative curvature. So for all the cases where you pack the thing on S3, the continuum theory is almost the same, right? You write a continuum theory with isotropic constant positive curvature, and you get to basically the same type of answers. However, there are also cases, especially icosahedra, even if you just pack 3 of them around an edge, the dihedral angle is so large that you always get overlap. And to get rid of overlap, you need a negative curvature. And you can only pack this in H3. And this is like you try to force them together in Euclidean 3D space, and it doesn't work. You see they overlap, right? So by introducing negative curvature, you can get a perfect crystal. It's the so-called 353 hyperbolic space honeycomb. It's a perfect crystal, and in this case, it is infinitely large. It's not a finite crystal like the 600 cell. And it looks really weird in this picture because I'm showing it using the Poincare ball representation. You have an infinitely large crystal, and on the surface, so this one in the middle is very large, but these other ones, in the actual hyperbolic 3D space, they are all equal sized. It looks like this just because I'm projecting icosahedron from infinitely far away to the surface of this unit sphere. The actual thing is a perfect crystal in hyperbolic 3D space. Okay? And then we can do a similar calculation of cutting a section from this hyperbolic 3D crystal. And in this case, we also cut a surface with no Gaussian curvature and ask what is the shape it takes in 3-dimensional Euclidean space. And from the same type of minimization calculation, we can find that it can be either a spherical cap, or this kind of taco-like structure, depending on the size of the cluster. And when you put the icosahedra actually on this surface, this is something that it looks like. Okay? So these are like 2 examples. So as you might think, like the assembled structures are somewhat complex, but still they're perfect crystal, right? Why do we say we can program complexity in this kind of self-assembly problems? They are not complex yet because we are choosing the simplest way to solve the problem. There are actually a number of steps here where complexity can come out in a rather controllable way. For example, the first step, how do you actually want to pack them locally? In the examples we show, we just say we choose a unique way. We want to close 5 tetrahedra. We want to close 3 icosahedra. Then you get a perfect crystal. But you can do many different things. And by choosing the polyhedra packing rule, you can get different types of non-Euclidean crystals. And this turns out to be a well-documented problem in mathematics. And you can go to huge tables to say, I want to pack in this way, what is the crystal? What is the curvature? Okay? And then another step is how do you solve the statistical mechanics of that problem? What happens when you put statistical mechanics together with the curvature? Right? This is like a whole new space of new problems that we have not explored so far. We only solved the very basic minimization problem. And then one other step is which part of the non-Euclidean crystal are you going to cut? Right? We only cut some very nice, smooth parts. But it's a really complex problem because there is a computation between the control of surface energy and also the natural tendency for the material to split due to stress. So when you cut complex boundaries, you can imagine that many complex shapes could emerge. And you can controllably program the complexity of these structures. You can choose a hierarchy of how you cut and how the thing split. Okay? So what we try to argue here is using non-Euclidean crystal structures, you can open up a whole new design space for self-assembly problems. Okay? So that is basically the first part of my talk, where we illustrate this recent work. We use non-Euclidean crystals to guide the study of self-assembly. So I think I'm almost running out of time. I will just very quickly go through some recent work we have been doing in studying mechanical properties of non-Euclidean systems. So the first work is to try to see what is the mechanical effect of having such a geometric frustration. So again, coming back to this analogy with frustrated magnetism. In frustrated magnetism, one property that people talked about a lot is ground state degeneracy, like you just mentioned. Right? So because of frustration, you tend to have a large number of ground states, either extensive or sub-extensive. And these large number of ground states give you a lot of tunability. If you add in a little bit of additional interactions or you introduce a little bit of fluctuations, you can bring new order to the problem and for example, have new topological states. So we would like to understand what's the effect of such frustration and the ground state degeneracy in mechanical problems, both in the frustrated assembly and maybe just in continuum elasticity. Right? So as a first problem, we choose to study this in continuum elasticity. So in particular, we choose to study the problem of thin elastic bodies. So it is known that if you try to describe the elasticity of thin sheets, you can write the elastic energy into 2 parts. A stretching energy, which has to do with the in-plane deformation, and a bending energy that has to do with the out-of-plane bending. And the in-plane elastic energy depends on the in-plane metric, and the out-of-plane part depends on the curvature. Okay? So it is known mathematically that there must be certain compatibility conditions between the in-plane metric and the curvature. And this gave us interesting compatibility conditions. And when you, in particular, when you choose the target in-plane metric and the target curvature to be such that they are don't agree with one another, they are not compatible with one another, you can controllably introduce a geometric frustration into the problem. So there has been well-developed mathematical tools to solve the morphology of these problems, such as in this paper and a number of other papers. So you can calculate what is the pre-stressed ground state, like this leaf. As you can see, there is some kind of geometric frustration. The material want to grow more and more fast as you go to the edge of the leaf, okay? And the new question we try to study here is what is the degeneracy of this kind of frustrated elasticity problem, and what can we do with this degeneracy? So to choose a solid example here, I don't want to go into too much detail, but basically we choose a particular family of thin elastic sheets. In this case, the so-called minimal surfaces. Minimal surfaces are defined as surfaces that minimize the surface area for given boundary conditions. And for minimal surfaces, there is a nice property that they come in these so-called associated families. So for example, here I show the family of helicoid and catenoid. You can label the whole shape family using a phase angle. By changing this phase angle from 0 to 2 pi, you get different shapes. And the nice thing between all of these is that they all have the same in-plane metric. As you go from one shape to another, you're only changing the curvature. You are not changing the in-plane metric. You're not stretching in plane for the material, okay? And then you can calculate the elastic energy. You will see that all of these are exactly degenerate, okay, when the sheet is infinitely thin. So this gives you a U1 degeneracy. You have a phase angle from 0 to 2 pi, which are exactly all degenerate. And then to make the problem more controllable, we introduce a little bit of more bias. For example, you can make the sheet a little bit thicker, and that can break this U1 degeneracy to a Z2 degeneracy, so that you have left-handed and right-handed helicoids that are the two true ground states. And then you have a low energy manifold where all of these are still low energy but slightly higher than the two helicoid states. Then you can write a low energy theory for that, which is something like this, where this phi is the phase angle, which describes locally the shape. This term tells you that you have two ground states, which are the left-handed and the right-handed helicoids. And this term is the spatial gradient. So if you're familiar with the continuum theory for solitons, you can immediately see that this elastic energy admits soliton solutions. And in particular, you can have solitons where the phase change by 2 pi, or solitons where the phase change by pi. And if you define the charge of the soliton by the change of the angle, the phase angle divided by 2 pi, then these are charge 1 excitations, and these are charge 1/2 excitations. And this turns out to be exactly analogous to these spin 1/2 excitations in dimerized spin antiferromagnetic spin chains that was studied by Houdin in 1980s. So in particular, you have two dimerized ground states, which are just shifted by one spin, right? And interestingly, you can break a dimer and have a spin 1 excitation, and then you can move them apart. Each of these is a spin 1/2 excitation, which is exactly analogous to what's happening in this classical 1D chain, okay? And then interestingly, the special property here is really that these excitations are extremely robust. And to illustrate that, we can compare it to, for example, solitons in a Sine-Gordon theory, which many of you probably have seen. Here, the only difference is this factor of 2. In a Sine-Gordon theory, you have this term that tells you that you have one ground state. You can change this phase angle by 2 pi, but it's truly one state, which is this spin point, this angle pointing up, okay? And the only soliton you have is to change by multiples of 2 pi. And we argue that this type of soliton, which is between left and right-handed helicoids, is more robust than this one, because here you can locally cut and reconnect the string and get rid of this charge 1 soliton. It is beyond the low energy theory, but you can do it locally. From far away, you would not know that this soliton went away, right? It looks exactly the same. However, here, you can never get rid of it because each of the charge 1/2 excitation separates 2 different ground states. Yes?
It's a nice thing to see quantum field theory over there. I'm wondering if you have a second-order derivative in your energy functional, would you still get solitons, all that stuff? This higher order derivative, higher order elasticity.
That's a very interesting question. I think so. Here, the soliton is
I think
more
it would
like
not change so much.
Yeah, probably, because here the soliton is more like an interface between 2 different ground states. When you add more orders of derivative, it changes the shape of that kink, right?
Second order derivative is like to consider extrinsic geometry in your plate like that.
Yeah, I think probably it still exists.
Okay.
Yeah. Okay, yes?
When we talk about edge states, always we are talking, we are thinking in self states, right? Because the zero states are possible in these systems.
Surface states?
No, zero energy states are possible.
Zero energy states.
Or the fact that the system is frustrated don't allow the existence of this kind of states.
Yeah. So for this particular example, the theory we will start with, you cannot have zero energy states in flat space.
Because the frustration.
Yeah, because of the frustration. Maybe there is a high-dimensional space where you can embed it nicely. We have not solved this particular problem yet. Okay. Okay, so here we argue that it has a very strong topological protection. And so then this is all theory, right? It looks mathematically interesting. Can we actually have an experimental system that does that? So to explore that, we collaborated with Alan Aruda's group at U of M, and we just 3D print a helicoid. In this case, actually, when you first print it, it's stress-free. But we print it in a right-handed helicoid state, and we twist it to a left-handed helicoid. It's a metastable state. But then, interestingly, I'll play the video. When you release it, 2 solitons actually get generated on the top and on the bottom. And they propagate to meet in the middle and annihilate one another. So then it stops. So let me play it again.
Which material is this one?
Sorry, well, oh, yeah.
Which material is this one that you are showing? What is that exactly that you are looking at? What material?
Oh, this material, it is Agilent 30. So it is 3D printed, some rubber-like material.
Okay.
Yeah. So for us, not only like showing this soliton exists and can propagate, it's really interesting, but also there are other features we learn by doing this experiment. For example, here the material is like a rubber. It's really viscoelastic and dissipative. And yet by using these solitons, which are topologically protected, we can get a wave that can propagate really far away. So normally in this kind of highly dissipative material, you would not expect a wave to propagate very far, right? But by using these fractional solitons, we can actually program an excitation that can go as far as you want with a constant speed because it is propagated on stored elastic energy. So it's really fun to look at how you can make use of these fractional excitations and program stable propagation of waves in dissipative materials. Okay, and there are other features. For example, it's holographic in the sense that if you have only one soliton, there is a one-to-one correspondence between where is this soliton under the twist of the tip. You can control it from very far away. So for this part, I would like to just argue that the idea is by using geometric frustration, we can introduce controllable degeneracy, and we can use that to program fractional excitations and the dynamic response. Okay? And at last, I will just briefly go over another recent work we did in studying what are the wave eigenstates in non-Euclidean crystals. So why do we care about that, right? So firstly, we say that these kind of non-Euclidean geometry can naturally arise in self-assembly problems when you have geometric frustration. And this example I show here is a two-dimensional hyperbolic lattice. So you imagine if you have hexagons, you can tile a nice flat plane, right? But if you have heptagons, which are seven-sided regular polygon, when you try to tile them together, they overlap. When you try to get rid of that overlap, you need to introduce negative Gaussian curvature, so you get a hyperbolic crystal. And here, again, we are showing it using the so-called Poincare disk model, where you project an infinitely large hyperbolic crystal to a unit circle. So these are very distorted, but the actual thing is perfectly ordered. Okay? And another motivation is that you have infinitely many choices of symmetries. If you limit yourself to crystals in flat space, there are only so many crystal groups you have, right? Because you need to put a rotational symmetry together with periodicity. However, in these hyperbolic crystals, you can have any symmetry you want. You just introduce enough curvature to allow that symmetry, right? So this gave us a lot more degrees of freedom to play with in terms of wave propagation. And there has been recently a lot of nice mathematical studies in what are the waves in these crystals. For example, in this paper, the authors showed that they studied this so-called 8-8 tiling, which is similar to this. So although the crystal itself is two-dimensional, in flat space, when you have a two-dimensional crystal, you know the Brillouin zone is also two-dimensional. You have two momentum. But here, the Brillouin zone is actually a genus 2 surface, and you have 4 momentum instead of 2 momentum, just by having hyperbolic geometry. And there are also a number of other studies of topological states and other interesting effects in hyperbolic space. So what are we trying to do here? The new fundamental question we try to look at here is based on a very unique property of hyperbolic lattices, which is the fact that the translation group of these lattices are non-abelian, which means that if you do translation operation on a flat crystal, we all know that you take a square lattice, you do translation this way, or this first, this second, you arrive at the same site, right? But this is no longer true in a hyperbolic crystal. You do translations in different order, you end up at different places. And this is the mathematical property that the translation group is non-abelian. And from group theory, we know that when you have a non-abelian group, there must be high-dimensional irreducible representations. This tells us that there is something fundamentally different when you try to solve wave eigenstates on these hyperbolic crystals. So just to be brief, this tells us that we need to generalize Bloch theorem. Bloch theorem is really like the cornerstone of solid-state physics, right? It greatly simplifies problems in flat space so that we know when you translate a wave function in a periodically potentialed space, you just need to multiply a complex factor. Here, instead of complex factor, you need to transform groups of waves together using a complex matrix. And then in this paper, we developed methods such that we can construct waves that carry these representations. And we can calculate band structures. And one interesting effect we found is that if you try to study edge states or any localized excitations on these hyperbolic lattices, you necessarily need to use high-dimensional representations of its translation group, because the one-dimensional representations has a property that it always repeats itself on certain subsets of sites. Okay, so here I would like to just summarize. We studied the geometric frustration in different setups, and we show that there are interesting physics at the interface between mechanics, self-assembly, and complexity. So I'd like to thank you for your attention.
Questions there?
So first, thank you for the talk. But my question refers to the first part of the colloquium, when you were talking about the structures that became from little tetrahedrons. I don't know if it's a trivial question, but I was thinking about why these structures sometimes scales with the size of the structure, and sometimes don't. Like in your example, this little spiral shapes that you did with little tetrahedrons, but in other examples like Nautilus shells, that structure scales, and in another examples you just make crystals.
Sorry, let me try to understand your question. So in which case you said it is scaled?
No, I just was trying to understand why in some cases that structures could scale with the size of the final structure, and sometimes don't, just form crystals, as you said in the first example of that chiral helicoidal structures that in little scales form that spiral, but when you go to macroscopic scale, just make normal crystals. Is it due to the geometric frustration, or don't?
I see. So I think if I understand you right, you're asking what determines the size of the clusters, right? Why sometimes it go to a large crystal, sometimes it doesn't. I think many factors come in. So we have not particularly studied that effect here, but there are other studies, not for non-Euclidean crystals, but other types of geometrically frustrated self-assembly. It is an interplay between the surface energy of that cluster and the bulk energy of how much frustration you have to overcome to make it bigger. So basically, by considering those factors together, you can find sometimes there is an optimal finite size. But sometimes I think the terminology they come up with is called escape. Sometimes it escapes to bulk crystals. It depends on both the energetics and the kinetics of the self-assembly process. Okay?
Thank you for the nice presentation. I have two questions. The first one, you talked about beginning to do statistical mechanics with the non-Euclidean space. And my question would be, the first step will be to introduce temperature and to see if the shadow of the higher dimensional structure still reflects what we see in our space. And the other question is to do with the cuts of also the higher dimension structure, because you said that only the smooth surface cuts count for the morphology, if I understand correctly.
Yes.
But the cuts are kind of arbitrary, for what I understand. You can cut many ways, right? So how do you make sure that only those cuts count?
Yeah, that's a very good question. I think we do not know what is the best way to cut. In some sense, we cut it in this way, guided by experiments. We see that you get these ribbon-like structures, so let's cut a ribbon from that. We also have put in a number of considerations, like along one of the direction, there is no frustration. So you can get along in one direction, but the other direction is frustrated. Actually, come back to the question of degeneracy. There is actually a degeneracy of choosing left-handed versus right-handed. And that is actually cutting along different directions in the 600 cell. It's interesting, the internal structure of the 600 cell is achiral. But depending on which direction you cut longer, which direction you cut shorter, there is a left-handed and a right-handed version. And there is a symmetry breaking when you combine that with the thermodynamics of the problem. So there is a spontaneous symmetry breaking of a left-handed minimum and a right-handed minimum. That is one example of what happens when you have thermal fluctuations. But when you have out of equilibrium thermal fluctuations, there are many problems you can study, right? How that guides you into cut a particular part. And after you cut that part, what's the symmetry breaking hierarchy of that assembled structure? It's all, nobody knows. It's all new problems. Okay?
Any other question? I have a question.
Yeah.
Connecting to the beginning of your talk, when you have shown these funny structures that we find on the sea, can I understand them? Could I understand them as being the ground state of a given structure if I allow for an optimization using some curvature?
So that would be really interesting. We do not know yet. So I think there might be a factor of that, or it might be just biology. We have not studied this. I sort of use this as a motivation to see how this interesting geometry arises in nature. But yeah, it will be really nice to understand it.
Okay.
Yeah.
Okay, so if there are no more questions, let's thanks again, Xiaoming.
Thank you.
That's beautiful, really nice. I haven't think about